annular array. It also has two crystals that oscillate at right angles to each other to give you real-time 3D ultrasound by virtue of a biplane scan where the two scans intersect each other. That means that you can do a longitudinal and a transverse scan on a split screen in real time simultaneously. This is very simple technology. This is cheap and conventional and very well proven technology. I'm going to demonstrate that part of it with this older embodiment. You'll notice that the crystal with the red post goes up and down, and the other crystal goes from side to side, and both scans intersect through their middles. Now what I've done in the new technology is I've taken out one of these annular arrays and I've substituted a curved array. Now the curved array gives us the advantage of having state-of-the-art color Doppler, and the way that works is that we simply position the curved array in a stationary mode, and that takes all the vibration which so compromises mechanical scanners' color Doppler. We simply put it in a top dead center position and let it scan as a conventional curved array. I'm going to stop the tape now, and when we come back I'll show you the new embodiment. Okay, here we are with the new embodiment. This is all to scale. This is a curved array in this area here, and this is in the magenta area here is the annular array. One thing I want to point out is that the curved array comes all the way down to the annular array without touching it, and as I cycle it back and forth, you see that there is no interference. Even though the curved array comes all the way down to the annular array, it does not interfere with the annular array. Also, the hinge which supports the curved array in no way impairs the function of the annular array, because the annular array does not begin to sector until the hinge which supports the curved array is completely out of the way, and at that point the annular array begins to sector. So I'm going to turn this on now and show you the function. This is very simple construction, and this embodiment also gives us the ability to do biplane scanning, but in addition, if we stop center, color dot curved array in the stationary mode. Now when we use the curved array in the oscillating mode, we also get full volume 3D. And the way we do that is we start out by directing a beam from the perimeter of the curved array, and as that beam travels in its oscillation, it creates a tomographic section, and then we simply step the point of origin of the beam over slightly for the return, and then continue to do this every time we pass through an oscillation, is simply step it over, And in that way, in a very short span of time, say in about a second or less, we've acquired enough tomographic sections that we can compile them on a CAD program, on a PC, or in a compiler on a CAT scan, and acquire a full volume 3D scan. In summary then, what we have here is the finest resolving power the laws of physics will allow, because we're using an annular array in this position. We're having state-of-the-art color Doppler by using the curved array in the stationary mode. We have real-time 3D scanning by using both arrays to do a longitudinal and a transverse section simultaneously on very cheap conventional split-screen technology. And we have full volume 3D by using the curved array to acquire multiple images stepped over and then compiled on a CAD. Now, all of this is brought to you at rock-bottom prices because this is a mechanical sector scanner. And mechanical sector scanners cost a fraction of what solid-state scanning systems cost. So we are capable of doing many more tasks than are currently available, doing them with superior abilities and at a fraction of the cost. This is nothing short of a revolution in ultrasound, and I invite you to become part of that revolution. Please get in touch with me. My name is Marvin Glover. You can find my phone number on the pamphlet which accompanies this videotape. Thank you very much.